Today we're gonna be doing the physics week 11 quiz. It's really easy this week. It's all about waves. Now let's start. Now first question, they're asking us, so sound can be defined as, now whenever we're talking about sound, we need to know one thing, or two things actually. Sound is always longitudinal, I forgot to spell, longitudinal, and it's always mechanical and only travels in a medium. Whenever you think of sound, these are the three first words that should pop up in your head. So whenever we're talking about sound, it's defined as a longitudinal wave, and it is mechanical because it's when you have a sound, its disturbance or its interference is pushing the particles around it, which are gonna go pushing the particles around that, which are gonna go pushing the particles around that. So there's pushing, so it's mechanical. And it obviously needs a medium because it's sound. Light, on the other hand, is transverse, it's electromagnetic, and it does not need a medium. It can work in a vacuum. So it's the opposite, practically, of sound. Now, moving on. So which of the following describes sound in air? Sound is longitudinal and mechanical. Like we said, these are the only two words that should pop up in your head when we're talking about a sound wave. Okay, so what are waves? Waves are vibrations. We already know this. Like when you throw something in a puddle and it's making a ripple effect. They transfer energy without moving matter. So, waves are vibrations. When they transfer energy, and you know this because you could see that the more you move away from the source, the weaker the lines get. So it's transferring energy, and the energy is being, I don't want to say lost, but kind of lost in the process from one place to another without matter being transferred. So you're not really transferring matter, you're just transferring that energy. Because when you have a wave, it's just moving the particle up and down, up and down. You're not really moving it any other direction. So that's it for this question. Moving on. Okay. So here they're asking us, so row A describes a movement where particles are spread out. Whenever you see the word spread out, it's rarefaction. Always, just think spread out, rarefaction. Like, I'm gonna draw it in a coil for you. This part, you would say it's rarefaction because they're spread out. Rarefaction. Now, but when they're closest together, like in this part, it's a compression. I can't really fit it. So whenever you see close together, it's compression. Whenever you see far apart or spread out, it's rarefaction. Now, whenever looking at a graph, whenever your peak is always gonna be compression, and your trough or the bottom most point is always gonna be rarefaction. Always. So in this case, which presents in row A, which was rarefaction, it would be Z, and description of row B, which was compression, would be X. This is really easy. Moving on. Okay. Whenever you hear frequency, frequency is how many waves are per second. So how many cycles, as they used here, per second. Now, wavelength is the distance from one wave or one peak to another peak. That's the wavelength. The speed or velocity, this isn't even a definition in waves. It's the distance per unit time. And the amplitude is the maximum displacement of a particle from its rest position. Now let me draw it in a graph for you. Your wavelength would be would be your wavelength. Your amplitude would be this, or like this, or whatever. That would be your amplitude. Speed, you can't really show it. Frequency is you'd say something like this would be 1 cycle, and the frequency is how many per second. Moving on. I feel like, yeah, I skipped it. Okay, so here, which graph is the loudest? Now, when we're talking about loudest, you need it to relate to amplitude. So the higher the amplitude, the louder it is. Now, if you look here, this is reaching the peak or the top of the graph. These aren't. So the one with the biggest amplitude would be B. So that is the loudest. Now, when we say the word pitch, we mean the one with the most frequency. And when you see a lot of cycles like this, it's the frequency. So D would have the highest frequency. Let me write it down for you. So pitch relates to frequency. The loudness would relate to amplitude. Intensity would be amplitude squared. It relates to amplitude squared. Okay, memorize these three. Now, moving on. Okay, so a wave where the displacement is along the same direction as the direction is called a longitudinal wave. Now, when we want to present longitudinal waves, we present them with graphs of lines. Where lines get closer, either closer together or farther apart. Or you're gonna see there's a question about it in a bit. But when we say transverse waves, we mean waves that go like this. So where it's along the same direction, they're moving along this direction, it's the longitudinal. Okay, calculate the speed of a wave. Now, there's only 2 formulas we need to memorize. Frequency is, in hertz, is the 1 over time in seconds. That's formula number 1. And then velocity is lambda, which is in meters, over time in seconds, which is the same as saying it is lambda times frequency. Lambda in meters, frequency in hertz. Now, the speed of the wave, so we have to use one of these 2 equations, depending on what we have. In the wavelength, which is lambda, is 25 centimeters. Frequency is this many hertz. So we have lambda and we have hertz. So we use velocity equals lambda times frequency. The speed in meters per second, so we have to convert this to meters. 25 centimeters would be 0.25 meters. So 0.25 times, so this is 0.25 meters, times 1200 hertz would give you 300 meters per second. And that's it for this question. Now, moving on. Which of the following statements best describes a transverse wave? Now, our options say the first one, the particles of the medium move in the same direction. When we said same direction, we always are talking about longitudinal. We're not talking about transverse. The particles of the medium move in a direction normal to the wavelength. Yes. Whenever you see normal to the wavelength, we're always talking about transverse. Energy is transported, yes, because it's an electromagnetic wave. so it's transporting energy with it. When we said the sound, it does not transfer energy, whereas light does. Sound are considered transverse? No. Particles of the medium can travel with this wave? Definitely not. Now, moving on. So, which of the following shows a periodic wave? When we're talking periodic wave, we mean have an equal wavelength. Like between this and this and this and this, they have to have the same wavelength. Here, obviously, as we can see, they do not. So this is the only periodic wave. And this is just a graph, and this is not even a graph or a slope. Okay, which of the following intervals represent the period of this wave? Now, when we're talking about period, we're talking about the time between two consecutive crests. So it's between either A, E, that's a wavelength or a period. We're talking also O, D, that's also a wavelength, because it's from this bottom to this bottom. And you could also say this point till this point, but they didn't give us a letter for this point, so we don't count it. But that would also be a period. So now we have AE and OD as our only two correct ones. Moving on. The number of waves that pass a fixed point in the medium per second. When you see waves per second, frequency. Only thing. It's a definition. Okay. So a train of pulses are a wave. When you have more than one pulse, it's a wave. Whereas a disturbance, when it's traveling through a medium, is a pulse. So when you have more than one pulse, you get a wave. When you have a disturbance, it is a pulse. And the point where there's a maximum displacement, when they're far apart, is a rarefaction. When they're close together, compression. Moving on. Okay. I don't know why. Anyways, this shows you, this is what a longitudinal wave looks like. Where you have points close together like here, and where you have points spaced far apart. Here also as a compression. But yeah. So this is a longitudinal mechanical wave because as you can see, particles are being moved, and it's an earthquake, so definitely mechanical. Now, underline which compressions and which are rarefactions. We said compressions are at 1 and 3 when they are close together, and that you have rarefaction when they're far apart. So here they're far apart, here they're far apart. After this point, you could see they're all periodic, so that's why you don't choose 5. Whereas look, this box is this big. This box is this big. This box is way bigger, so this is a rarefaction. This also is way bigger than whatever this is. These, you can barely see boxes. So 5 would be neither because they're all periodic, they're all the same length. 1 and 3 obviously compressions. These are rarefactions because you can see they're huge boxes. That's why you don't choose 5. 1 and 3 compression, 2 and 4 rarefaction. Okay, now about speed. We need to know a few things. The speed of sound is always less than the speed of sound is always less than the speed of light. Always. Now, we need to know that sound, or let's start with light. Light travels fastest in gas, then solid, then liquid, then solid. It travels in this direction from fastest to slowest. Now, sound, on the other hand, travels fastest in solids, slowest in gases. Okay? Memorize these. So the speed of sound in water is greater than the speed of sound in air. Liquids and gases, of course. The speed of light in water is less than the speed of light in air. because we said gases are the fastest. Air is a gas. So, yes. The speed of sound in water is less than the speed of light in water, because we said the speed of light is always faster than the speed of sound. The speed of infrared radiation in air is equal to the speed of visible light in air, because they're both in air and they're both electromagnetic radiations. Or, yeah. Moving on. Okay. For this question, you have to read it very carefully. Now, you have the satellite laser ringing service. Uses short pulse lasers and the sensitive timing devices to measure the distance to the satellites orbiting the Earth. The laser pulse emits from Earth, reflects from the satellite, and is detected by a sensitive sensor on the ground. So what they're telling you is the satellite sends out, or the thing on the sensor on the ground sends out and waits for it to receive a signal back. So it sends and receives one, so it's going twice. Now the laser signal returns to Earth at this speed. The wavelength used is this many nanometers, and the speed of light is this. Now, they want what's the altitude of the satellite above. Altitude is measured in distance, so altitude is lambda. They gave us the velocity and they gave us time. Now, what do we know? Velocity equals lambda times frequency, right? And we know that frequency is 1 over time. And since frequency is 1 over t, so the frequency here is 1 over 1 times 10 power negative 2. Okay, that's your frequency. And we know that we want lambda, so lambda, so it's velocity equals frequency times lambda. So lambda is velocity over frequency. Okay? So velocity is 3 times 10 power 8, because that's the speed of light, over 1 times 10 power negative 2, which is the same as 3 times 10 power 8 times 1 times 10 power negative 2. They're the same. When you do this, you're gonna get 3. Let me check on my calculator. You're gonna get 3. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So you're gonna get 3 million. Now you're gonna say, okay, that's my answer. But wait, what did we say in the start? We said that this is from the sensor to the satellite and back. This is the distance from going and back. So if you want the distance of only going, you're gonna have to divide by 2. When you divide by 2, you're gonna get your answer equal to 150. 1, 2, 3, 4, 2, 3, 4, 5. And they're asking us in kilometers. In kilometers, you remove 3 zeros. So you're left with 1,500 kilometers. And that's your answer. So first of all, memorize this formula and this formula. What did we do? We found our frequency. And we rewrote our formula in this way. And then we solved using the frequency we got and the formula. Now, why did we use electromagnetic waves instead of sound waves? So why did you use light waves or whatever waves that are electromagnetic rather than sound waves? It's because sound waves do not work in vacuum. And we know anything in outer space is in a vacuum. So electromagnetic waves can travel through empty space, whereas sound waves cannot. Now moving on. Okay. They're asking us the period of this wave is about. Now, to find the period of the wave, you're gonna have to look from one crest to another. So you have to go up, down, and back up to this point. This is 1 period. Okay? So since this is 1 period, how many seconds did that take? You go down and you see this is at 0.4 seconds. So that's your answer. You could also look at this and they'd still give you 0.4. But I'd prefer looking from this to this. It'll give you 0.4 as your seconds or time. Period. The frequency of the wave is, so to see the frequency of the wave, it's we said frequency is 1 over time. So its frequency equals 1 over 0.4, which if we do it on our calculators is 5 over 2, which is 2.5. And that's your frequency. The amplitude of the wave is the highest point on the wave, the crest. So it is, each one is 0.1. You have to do 1, 2, 3, 4, 5 to find out. So there's 0.5 and each one is 5. So each one is 0.10. So this is 1.1 and this is 1.2. And that's your answer. Our answer is 1.2 centimeters. Now, moving on to the next one. Now, which of the following is the propagation in a rope? This is a rope. So we have a transverse wave, of course, since it's in a rope, or since it's going up and down. It's transverse. And since you are moving the rope, it's a rope, so you're moving it. It can't move alone. It has inertia alone. It can't move. So once you move the rope, it's mechanical. So it's a transverse mechanical rope. And they're asking the wavelength. We said we check the wavelength by doing from here to here. And this is about somewhere like 0.63, you could say. Like you have to actually account, but the closest option to this was 0.63. Because this would be 0. Wait, I didn't count the factor. 1, 2, 3, 4. 0.2 divided by 4. Each one is 0.05. So if you reach here, it would be 0.65. So between the two, the closest thing in the options was 0.63. So that's your wavelength. And the amplitude, we said, is the highest point, which is at 20. Moving on. Or here it's 20 centimeters. So it's 0.2 meters. You have to convert. Okay. The property of the sound determined by the wave amplitude, we said this when I drew it out for you. It's loudness. So, loudness is closely related to amplitude. I'm just going to write amp. And the rate, the rate the wave carries is sound intensity, because it is, sorry guys, whenever you see the rate and the wave carries energy through it, it's sound intensity. And the one that depends on the frequency is pitch. So pitch, closely related to frequency. And the last one is definitely sound intensity. Now moving on. Okay. Where if you increase the frequency, we said pitch will increase. The property that changes the amplitude of a sound is increased, so it is loudness. Now look, the amplitude of the sound is doubled. We said that intensity is related to amplitude squared. So if your amplitude was doubled, you have 2 amplitude now. So 2 squared is 4. Amplitude squared. Right? So if you multiplied it by 4, how much would this? You would have to multiply this by 4. So whenever you double amplitude, intensity will multiply by 4. Or like the squared of how much you increased it by. It quadruples. So the amplitude of the sound wave is doubled, the intensity will quadruple. That's the end of this quiz. Hope you understood everything. It's really easy this week. Have a nice day. Bye.